Acha, just load it first of all. Yeah,
A very pleasant morning to one and all present here. It is my pleasure to welcome you all for today's program. I request all the dignitaries to come to the stage and take their seats on the dais. Dr. Fabiola Ginotti, Shri K.N. Vyas, please. Professor Ashutosh Sharma, on behalf of him, Dr. Praveen Asthana, Dr. K. Kasturi Rangan, Dr. Arun Srivastava, please. I would like to invite Shri Arun Srivastava, Secretary, AEC and Head, ICPD, NCPW, and DAE, to formally welcome the gathering.
Yeah, okay. Good. Good morning, everyone. And I'm so happy to see a large audience over here. And very happy and thankful to Fabiola, Dr. Kasturi Rangan, Vyasji, everyone to come. And I see a lot of dignitaries. I don't think I can describe their position over here. High-level people to grace this occasion. So I welcome all of you to this program, which we have specially organized this time. And Dr. Fabiola, special thanks to you because you have traveled more than 15 hours one way and managed to come here for 24 hours. That's really very remarkable. I can only say that the CERN exhibition, which was initially we decided to put up in India, that has come up very well. Adding to that flavor, we added the other mega science programs which India is participating. And so that has given a little bit more impetus on what India is doing. We have tried to symbolize the entire thing through one of the posters, maybe you can see a little bit later, where all the projects and their necessity are described. Because this question which is normally asked as to why India is participating in several projects. I'm sure this question is being asked in practically all the countries or the members. Why so many projects? Everybody looking at the universe. So we have tried to get an answer in a short span. And I'm happy the way a response has come. We have our venue partner in National Council for Science Museum, who have been able to provide such a lovely venue and a constant stream of science inquisitive people who could make it to this place and see it. I'm sure when you move around, you'll find a lot of students from various classes who will be coming over here. So it's a fantastic thing which just happened. Initially, we had a doubt whether even for 7 days we will be able to last. But the way it has come about and the blessings of such high-profile people attending this program, ready to grace the stage during the inaugural program, actually made us more confident that yes, such things can happen. And in fact, there is a request that we should take it to Tier 2 cities. Why only metros? And we do plan to have it. And NCSM has gracefully agreed that after we are done with Delhi, they will own the entire exhibition and take it to all their venues where they have it. So thank you very much and welcome all of you. We'll now have a traditional lamp lighting before we formally start with other activities. Yeah.
Thank you, sir, for your earnest welcome address. Now I request the dignitaries to kindle the light and symbolically inaugurate the program.
शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते दीपज्योतिः परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिः परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापं सन्ध्यादीपनमोऽस्तु ते
Thank you all for lighting the lamp. I would now like to call upon Shri K.N. Vyas, Chairman, AEC and Secretary, Department of DAE, Guest of Honor, to address the gathering.
Good morning to all the dignitaries on the dais, dignitaries of the dais. I was promised that by Mr. Arun Srivastav that I will not have to speak here. But then when I saw my name here, I realized, because primarily I have come to greet Dr. Gianotti, because if what I could make out is if she can take such a long flight, at least my flight duration is about 1 hour and 25 minutes, so at least I should be present here. First of all, I would like to thank CERN and basically all the colleagues for giving us the basic seed using which this exhibition was sort of envisaged. Secondly, lot of effort, because when you have to do something for the first time, because it's for the first time in India, such an exhibition on mega science activities has been is being planned and it is organized. So the amount of effort that has been put both by Dr. Asthana as well as Mr. Srivastav and in their respective teams is also tremendous. In Mumbai, the amount of footfalls were extremely high. That gave us a full idea that yes, this is going to be very well received all over the country. We are, as you know, it is going to travel to 4 locations. Mumbai is already over, Bangalore it is going on, then Kolkata, and then New Delhi. One more sort of, I would say, keenness which I have basically I do not know much about science. I am an average mechanical engineer. So I was very keen that Indian industry is capable of developing lots of equipment and which can be used in some of the mega science project. So we were very keen right in the beginning that Indian industry, they participate, they try to understand with the specialists who are representing the mega science projects one by one, and then we are able to gain something out of that, because when we try to do anything little difficult, it improves our own confidence as well as our own quality of our standards which we have to meet. So I hope that this long duration of exhibition which is there, a lot of interactions are taking place, and I invite all the students as well as industry persons also, if they want any information in future, please feel free. They can either approach Department of Science and Technology or Department of Atomic Energy, any of us, to give clarification, and I promise that we'll certainly give you the required information, whatever that you feel is going to be helpful. So with this, I would sort of stop here. Thank you very much, and I'm sure we'll be all waiting for her presentation and her lecture. Thank you.
Thank you, sir. Next, we have the address of Professor Ashutosh Sharma, Secretary DST, read by Dr. Pravir Asthana, Head, Inspire and Mega Science Division DST.
Dr. Fabiola Gianotti, DG CERN, Dr. K. Kasturi Rangan, former member Planning Commission, Sri K. N. Vyas, Chairman Atomic Energy Commission and Secretary DAE, my other colleagues from DAE and DST, ladies and gentlemen. First of all, my sincere apologies for not being able to be present on this important occasion. I would like to assure you that I had made all the plans to be with all of you, but some unexpected and unavoidable engagements have suddenly come up and have prevented me from traveling to Bangalore. I have requested my colleague from DST, Dr. Pravir Asthana, to read this brief message before all of you on my behalf. We are thankful to Dr. Fabiola Gianotti, DG CERN, for taking some time off her busy schedule and paying a visit to Vigyan Samagam at Bengaluru. Her visit is important and significant for a number of reasons. Let me mention a few of them. First, the idea of having this mega science exhibition, Vigyan Samagam, started with a proposal to bring the CERN traveling exhibition, Accelerating Science, to India. I am told that this exhibition has traveled outside Europe for the first time. My colleagues in the DAE and DST then worked on the proposal and enlarged the scope to include all the mega science projects in which India is participating at the present time. Visit by DG CERN to the exhibition was therefore important, and I am glad that it has happened. Second, it was India's participation in the construction of the Large Hadron Collider, starting from the early 1990s, that started India's involvement in such mega science projects. It established the basic principles of collaboration in such projects, especially the paradigm of making in-kind contributions. It also established the mechanisms for managing such projects within the country. It was therefore important for the India's CERN engagement to be showcased before the general public, and we are extremely happy that DG CERN herself has decided to deliver a public lecture. I am sure, as the chief of the largest scientific laboratory of the world, we would hear from her what it takes to build, operate, and maintain such facilities, and also the exciting and front-ranking scientific results that come out of experiments at such facilities. Thirdly, India is now an associate member of CERN. It is our desire that the participation of Indian industry in the developmental activities at CERN should increase. We realize that this would require some special efforts. The ILO from India has been appointed, and he is disseminating to the Indian industry the opportunities available to them at CERN. He is interacting closely with CERN colleagues. We are constantly discussing how to enhance this further at the Indian end. It will be nice to have ideas, inputs, and help from the CERN management on this. I am sure DG CERN will have some suggestions regarding this. Finally, I must mention that Dr. Fabiola Gianotti's presence at Vigyan Samagam and her public address will be of great inspirational value for all the women scientists of this country and all our young girl students who aspire to be scientists someday. Who can be a better role model than her, an eminent particle physicist and head of the world's largest scientific laboratory? Like in all other nations, we in India are also concerned about the participation of girls and women in science and technology. The government of India has started several programs to increase their participation. We find that the numbers are impressive to start with, but the numbers drop significantly as one reaches higher stages. As these problems are similar across nations, it will be important if Dr. Fabiola Gianotti is able to share some thoughts on this global challenge. Thanks, everyone.
Thank you, sir. I request Dr. K. Kasturi Rangan, former Chairman, ISRO, and former Secretary, Department of Space, to deliver the keynote address.
Is the control? This is the. No, this is the. Let me just see. Please don't put anything here. Good morning. I am really privileged to be here today morning at this very important and august occasion of the Vigyan Samagam being organized by two of the leading scientific establishments of this country, the Atomic Energy Commission and the Department of Science and Technology, together with the National Council of Science Museum. I don't have to say much about these institutions. The DST, of course, has been the pioneer in promoting science and technology in this country virtually since the science and technology activity started in this country since its independence. And, of course, atomic energy with a vision to develop this capability, but not only in the context of energy production, but also in the context of inspiring several aspects of fundamental physics research, including particle physics, came into being with the vision of Dr. Homi Bhabha. And between these two establishments today we have one of the most formidable system of scientific research in this country. And I would like to congratulate both these departments. Of course, we have Professor Vyas here with us, the chairman of the Atomic Energy Commission. He has just taken over, but he has already made his presence felt in the Atomic Energy Commission's activities. I'm so happy to see him here. He has been not only promoting and accelerating the process of establishing the nuclear power in this country, but many other aspects of the nuclear program in this country, whether it is related to radioactive isotopes, the working of the fast breeder reactor and things of that kind. And also the fact that he is also having a very good outreach program, and this is an excellent example of that outreach program. And he's obviously ably supported by his colleague, Mr. Arun Srivastava. I know him for many, many years. A wonderful person to organize, visualize, and also has a good base in the context of pushing science and technology activities. So we have these representatives, and then, of course, unfortunately, we don't have Ashutosh Sharma today, but he's able representative again. Here, Mr. Hassan, Dr. Asthana is here. We have worked together for a long time on many aspects of policies and other kind of activities. So we are happy to have you, Asthana, here for this important occasion. And of course, NCSM has been also a partner not only with these scientific departments, but also with the department. I come from the Department of Space, and so I'm very happy to see that this institution is hosting this activity and also taking forward many of the related aspects to a bigger, larger cross-section of the society. It's certainly a very innovative approach, the very concept of this exhibition. And what is very important to see is that it is representing 6 or 7 mega projects which the country has now undertaken in the recent past. The important thing is that it has also, as Dr. Vyas mentioned, has left in the amount of interest that it has elicited in the common public. It's after all a very large investment. If you take into account all the 6 or 7 of these projects, probably, I don't know, it's a guesswork, that it could, in terms of funding, could exceed most of the scientific funding of this country for several decades. So that is the kind of a commitment that we have made in the context of this. But then its importance is very clear in the previous projection that was there, the rendition of beautiful Big Bang to the evolution in the early phase of the universe. And it looks to be that these science projects are getting into the mega science to go early and earlier. So that is how it looks like. So most of the programs are of that kind of a thing. And obviously the interest is tremendous among all generations, whether it is the youngsters, whether it is middle-aged, whether it is literate, whether it is illiterate. There is a fascination about what is going to come out of science with this kind of a thing. And certainly we should make sure that we understand this in the context of India's economic growth. And when I talk of India's economic growth and the ability to fund these kind of major science programs, I would like to particularly look at what has happened over the last 50, 60 years. If you really look at it, We had a 3.9% GDP growth early in 50s and 60s, and then it transitioned into in the 80s to 5 to 6, and now we are talking of 7 to 8% and so on. So if you see this, and also along with this kind of a growth, we see the scientific policy resolution, which was first adopted in 1958. 1983, it was a technology policy resolution. In the age of 2003, it was a science and technology policy resolution. And ultimately in 2013, it was science, technology and innovation policy resolution. And also more recently, the government has set up a Prime Minister's Science, Technology and Innovation Advisory Council. These are some of the major milestones in the act in the context of how the science has evolved over the years, over the decades. And along with that, of course, has been the establishment of the various science and technology activities in this country. So you have the early phase when the GDP, 0.5% of the GDP was not being allotted to the science and technology activities. You have multiple institutions created, basic research was supported, scientific education was brought into picture, and agricultural research certainly found an important point. It moved over to visible societal impact systems. We have agriculture, atomic energy, defense, space, biotechnology. Many of these came into existence either through a governmental department or through other kind of supportive systems. And finally, we are moving towards a 2% kind of a GDP the allocation. In the case of this, in fact, most recently, the government had been discussing the National Research Foundation, which would be a major step towards bringing in the university system, 800 odd universities, into the research fold in a substantial fashion, besides, of course, strengthening the research and scientific establishments of the various institutions under atomic energy and many other kind of a thing. So this is the story that has unfolded over the last 50 to 60 years. And obviously, with this kind of a background, what is important to note is that an early recognition of science and technology is at the heart of the related development strategy that has enabled India to create capabilities and capacities to promote science and technology in a variety of domains. Broad spectrum science and technology represented by DST, represented by DBT, represented by Earth Sciences and many others. Then there are very focused systems like the atomic energy, space, defense research and so on. Mega science is the natural evolution of these national endeavors along two tracks. One, national to global projects. So there have been several national projects, including in astronomy, in fundamental particles, and many other areas. Now they are all turning out to be global projects, a part of a global community which is coming together to put resources and other kinds of support for creating this. Then individual institution to multi-institutional network. In our own country, we are witnessing this aspect of several institutions coming together. The recent AstroSat, a very famous, very forward-looking astronomical observatory, is a classic example of several institutions coming together to build an astronomy observatory. And of course, there are very good examples on the classical side, both in the DST as well as in the atomic energy in this connection. The other aspects of these obviously are talking about the frontiers of science. Technological engineering fronts, the frontiers of complexity, therefore, involves large-scale investment, whether it is financial or human. So we see the program of the mega science projects in this. Of course, in the listing of the mega science projects, International Thermonuclear Experimental Reactor, which is very much in the advanced stages of progress, Large Hadron Collider again, so 30-meter telescope, we are working with Caltech, square kilometer array with Australia as well as with South Africa, and of course as a global system, India-based Neutrino Observatory promoted by Atomic Energy Commission with Tata Institute of Fundamental Research, laser interferometric gravitational array working with the United States. And of course, I don't want to say more about the space mission, but there are also missions which are in the planetary domain, which certainly will become mega projects in the years to come in the context of a global nature or the international nature of the collaboration that we will foster. Coming to ITER, its objective, of course, most of you know here, is to demonstrate scientific and technological feasibility of energy using fusion technology. It will, of course, generate 500 megawatts of power for 300 to 500 in the very first level, 500 seconds, with amplification of something like 10 with deuterium tritium. The use is magnetic confinement approach, tokamak, to produce fission in the high temperature deuterium tritium plasma, 150 million degrees centigrade. You can look at some of the things. One important thing about these kind of projects is the fact that atomic energy over the years developed industries in a very big way in supporting its own programs in the power projects as well as in many other areas. The industry today has a tremendous base with respect to the various high technologies, thanks to this initiative of the atomic energy. So what I have tried to do is to put here some of the important things that ITER has received from the Indian contribution, whether it is cryostat, whether it is cryo distribution, whether it is first consignment of cooling water pipes, and many other kind of a thing. What is important to note in this kind of a thing is the fact that we have a large cocktail of high technology systems which are critical for the operation of ITER, which has come from India. And what is also interesting to note is the interest that the industries have elicited to even support much higher levels of contribution to this major project, the international project in the thermofusion reactor. And I should compliment atomic energy for this kind of a improvement that industrial base has brought about through their demands of the highest level, not only in the context of the complexity, but also in quality, reliability, and things of that kind, which are very critical in the context of accepting these kind of technologies by an international body like ITER. What are the benefits for India? Science, of course, leapfrogging Indian domestic fusion program. We had the Aditya and SST-1 at the Institute of Plasma Physics in Ahmedabad. Burning plasma to fusion device in a 20-year kind of a leap that we will have. Technologies, of course, full access to technologies, contributing 9% of the total cost. So ITER documentation are open to members. Domestic industry, equipment of in-kind contribution made by Indian industries, many first of them steps forward in capacity and meeting international quality standard. This is very critical, but most importantly, the domestic industry has rose up to the occasion in supporting this. And human resources, very critical opportunity for Indian scientists to participate in the overall R&D and realization of a total system through direct and indirect participation. I go to the next major project, the Hadron. I'm sure we will have more of it to be heard from the Honorable Director General of the CERN. But I would say that it is to answer some of the very fundamental questions, the basic laws governing interactions and forces among the elementary particles, the nature of space and time at the earliest epochs of the universe. You saw that in the earlier rendition that was provided by the DST, and examining the physics beyond the standard model. This is the TeV range. The most important thing is that this is going to probe the universe at something like 10 raised to minus 12 seconds of its birth, and at a temperature which is something like 10 raised to 16 degrees centigrade. So that is the kind of a thing. Already one is talking of recoveries like quark, gluon, plasma, the early phase of the universe again, a new boson consistent with the Higgs boson concept, that the Higgs boson. Test of supersymmetry theories that match closest to the standard model, which standard model currently, with some departures, of course, it is still an accepted premise. The LHC configuration, of course, is the most powerful particle accelerator. I don't have to say this here. With 27, I'm sure most of it will be said by the Honorable Director General. 2 adjacent parallel beam lines and a total collision energy, proton-proton collision of 14 TeV. And with a Lorentz factor which will be 7460. So of course, there are 7 detectors. 4 of the more prominent ones include the Atlas, CMS, ALICE, and all that. These are all to look at the specific areas like the origins of mass, clues to the nature of dark matter. And what is important to note that the contribution that the Indian scientists have made, I will come a little bit later, but in the compact muon solenoid, India has played a very significant role, at least for studying the quark gluon plasma, and LHC, we will seek the answer to what happened in the missing antimatter. Again, the contribution from India in the LHC has been very substantial. You can see some of the examples of these character magnets, quenching motor, but these are all related to magnetic and other kinds of quenching system, power systems, and things of that kind. The most important thing to note is that as an expert support for the superconducting dipole magnet measurements, 100 man-years have been provided for by India. Support from the large, again, for the LHC hardware commissioning, we had given 20 man-years. 16 man-years have been already completed. And what does it mean in terms of the overall benefit that we have gained? Immense experience in commissioning our own high-energy accelerator. We have a very ambitious plan with respect to the accelerators development for a variety of research purposes. And in particular, India is actively participating in the development of the LINAC-4 for the luminosity upgrade of LHC in the click test facility, which is related to the post-LHC electron-positron linear colloidal program. The Indian industry and experience in handling big data, this is one of the important things. In fact, I should say about 100 PhDs have been generated in the idea of high energy physics in the collaboration with CERN. It's a very creditable thing for atomic energy to produce this kind of a high-level manpower. And India has played an active role in the development of worldwide Lhc computing grid. This is another important thing. It has two operational LCG centers, again computing grids, one at Calcutta and the other at Mumbai. And it also involves something like 14 universities. I come to the third important thing, which is the 30-meter telescope, to build and operate one of the most ambitious and powerful terrestrial telescopes to probe the early stages of auroral and to understand the predict. This is the largest telescope, one of the largest, if you may say so, and we are closely working with Caltech in the development of this particular telescope. We also, as usual, about 10% of the project cost, we are bearing it, and this is led by the ADs in Bangalore, the Indian Institute of Astrophysics, as well as the Inter-University Center for Astronomy and Astrophysics. And of course, the scientific goals are identity and reveal the nature of the first. Again, the early epoch of the universe, the reionization processes, and the distribution of distant stars and galaxies, unravel the nature of the dark matter and darkness. This is one of the key elements in the futuristic research in the context of the early phase of the universe and the related cosmological aspects, evolution of large-scale structure. Then star-forming study, and the other interesting aspect is the more recent developments with respect to looking for planetary systems around the other stars, the Kepler and other satellites, which have already come out with some very startling discoveries of the existence of various types of planetary system. But this particular will push that kind of a domain to something like 140 parsecs, and it can detect elements and molecules of the planet's atmosphere, something the first signature of the possible creation of life, to infer the presence of life. The TMT configuration, I won't go into the motor. It's a Lhc design, the hyperboloidal main mirror, a secondary mirror, as well as a plane mirror, and so on. What is important for us is that we did contribute to the primary mirror control systems. These are some of the most intricate technologies that we have developed, and it has to also undergo a very rigorous test and acceptance philosophy at the Caltech end before they received this kind of technology. And I should say with pride that we have come through this kind of a thing in the support of this TMC, primary mirror control, segment support, and coating systems and observatory software, including the telescopic control. These are some of the key elements that India is supporting for this. I go to the next one, which is the Laser Interferometric Gravity Observatory, the Indian component, a unique Indian participation in gravitational wave detection. The gravitational waves, of course, traveling space-time ripples are the fundamental prediction of the Einstein's general theory of relativity. Existence of the gravitational wave inferred much beyond, which is the Hulse and Taylors on the binary system with a neutron star and the quadruple nature of the radiation of the gravity were all detected through the reduction in the orbiting period, and they got Nobel Prize for it. The first time that indirect evidence for the existence of gravitational wave was there. During the past 2 years, 4 gravitational waves have been discovered with the LIGO itself. More recently, an evolved neutron star mergers have been done. This year's Nobel Prize, of course, the recent Nobel Prize went to this kind of a discovery. I want to say only one important thing here. Again, sorry. One is India is going to host the third node for the LIGO. This is extremely important from the geographic point of view, triangulation and those kind of approaches, so that you can stretch the baseline. And India has the advantage geographically to allow fine sky, and is fine enough for sky's localization of the sources. This is one aspect of it. Then, of course, the location has been already identified in Maharashtra near Nanded. The third aspect is the fact that there has been a tremendous, more than a decade of research work related to what kind of signature that one will be looking for when you talk of a gravitational wave and it is being detected. And it is where Professor Durandar and his group at the Inter-University Center for Astronomy and Astrophysics, the ICTS in Bangalore, the Raman Research Institute, they have been all working for decades in this kind of trying to, these are some of the most intricate and extraordinarily complex calculations involving general theory of relativity activity. And these were the ones that were basis for really identifying the genuineness of the signals that were received. So I should say again that here the Indian contribution has been more than just locating it and also providing certain level of technology for this, upgrading that LIGO for the next generation system, but also the work related to evaluating the kind of structure that the signals will have, and the most intricate calculation that were carried out by the Indian scientists in this particular connection. I quickly move to the next one, which is related to the square kilometer array. It's a 10 each and 700 million effort in the. But what is more important is what will be the largest telescope. 30 times more than the collecting area of the present one, which is 1 square kilometer, and it will be 50 times more sensitive to the largest telescope today. Key scientific problems again: dark ages, origin of evolution of cosmic magnetism, cradle of astrobiology, and strong field, and so on. India's important things are state-of-art controlling and monitoring system. The entire system for control and monitoring is being which is the brain and nerve center of the observatory. This is called the telescope manager, is being built by India. Development of subsystems for central signal processor, data and transport, and development of precursor activities, including modeling, theoretical studies, including utilization of SK data. I come to the next one, which is the Indian National Neutrino Observatory. Again, a mega project. This is being done by the initiative of the Atomic Energy Commission and working closely with the Tata Institute of Fundamental Research. This observatory aims at realizing a world-class underground laboratory primarily to study atmospheric neutrinos as a part of non-accelerator-based high-energy and nuclear physics research in India. It seeks answers to the seminal question of neutrino masses and mixing parameters, one of the most open questions today in physics. The experimental setup is the observatory is an ion calorimeter. 50,000 tons of magnetized iron is what is being used, going to be used, arranged in stacks and so on, which will be an underground laboratory located 1,300 meters below. And at the present time, the conceptual design of INO is very much in advanced stages, and also the initiation related to the activity on this will also start very shortly. And this will be one of the major observatories looking for questions for some of the very fundamental questions of neutrino physics. And of course, it will be available, I am sure, for international collaboration and cooperation as and when it is made operational. I would like to close this presentation by first of all telling that we are going to be living in a very exciting era with this kind of mega projects dominating the country's scientific activity in the years to come. This is number one. Secondly, it provides, of course, for all of us of the previous generation and probably the present generation, a lot of excitement, keen to follow what is happening, and a little bit of our own touch of how things are when we started this kind of a thing, but which has taken it today gigantic proportions. The last point, of course, is the tremendous enthusiasm that we are witnessing among the younger generation. And if the idea of promoting science and a scientific chamber among the next generation is one of the key objectives of this government and this country, certainly mega science projects are certainly an important answer to that strategy. So I would close by telling that a key imperative to fulfill the holistic goals of the Make in India initiative of the present government is to transform India into a 21st century knowledge society. An important element of such an knowledge society is its ability to successfully conduct missions like mega science that place highest demands on the intellectual and professional abilities of individuals, institutions, and nations. Thank you.
Thank you very much, sir, for a very informative presentation and talk. Now it's time for the public lecture. I consider it a great honor to welcome our chief guest, Dr. Fabiola Ginotti, Director General, CERN, to address the gathering.
So thank you very much. I'm very pleased to be here in the presence of the highest authorities of the Atomic Energy Commission and DST. and on the occasion of this exhibition, which covers not only CERN, and we are very honored and pleased to be part of this initiative, but also many other high-level scientific projects. And I think that the common thread, the fil rouge that links these projects together, is the fact that they are develop complementary approaches to understanding the fundamental and open question in physics today. And at the same time, in order to achieve their scientific goals, they need to develop cutting-edge technologies, and so have very, very strong links also with industry. So here we've heard a very nice presentation of these projects before. Here I'm going to tell you in a bit more detail what we do at CERN in terms, of course, of fundamental research, which is our primary mission, but also in terms of education and training of the younger generation, technological developments, impact on society, and international worldwide collaboration. So let me first remind you that CERN is the largest laboratory for particle physics in the world. It's an intergovernmental organization based in Geneva, in Switzerland. Our primary mission is fundamental research in particle physics, and particle physics is the most fundamental of all sciences, because we study the indivisible constituents of matter and of the universe, so the so-called elementary particles. And these studies over the decades have been recognized and awarded with many great discoveries. The last one is the Higgs boson in 2012. I will say a little bit more about that later on. But also by Nobel Prizes awarded to scientists working at CERN. The second important component of CERN and many other projects that you will see in the exhibition is that our scientific goals are extremely ambitious, and they require the development and the operation of cutting-edge instruments. In the case of particle physics, in the case of CERN, these instruments are in three main domains: particle accelerators, particle detectors, and big computing infrastructures. And they are based on cutting-edge technologies in many domains, from superconducting materials and magnets to big data, from fast and radiation-hard electronics to vacuum technology and cryogenics, etc. And these technologies are transferred to society to the benefit of life in general. So everybody knows that the World Wide Web was developed at CERN in 1989. And then, of course, since then it has changed society in some sense. Just a few months ago, we have celebrated the 30th anniversary of the web at CERN in the presence of Sir Tim Berners-Lee, who developed the web at CERN in 1989 when he was a CERN staff. The web is only one of the examples of the spin-off of CERN on society, so I will show some other examples, for instance, in the field of medical applications. Another important pillar of our mission is also the training and education, training of scientists, so physicists, engineers, but also the training of technicians and the education of high school students, high school teachers, through a large number of initiatives that I will mention later on. And last but not least, CERN is also a concrete example of peaceful collaboration across the world, because it attracts some 18,000 scientists, more than 110 different nationalities. And actually CERN was founded in 1954 by some visionary European politicians and scientists, with the goal on one end of bringing back scientific excellence and excellent research in Europe after the war. And so these people already understood that the economic growth and the renaissance of Europe after the war also starts from great science and great research. And the second goal was to foster peaceful collaboration among European countries after the divisions, after the difficulties and the fights of the war. And today CERN has 23 member states. They are not only European, mainly European, but we also have, for instance, Israel, a non-European country, 7 associate member states, and India is one of them. We are very proud of it, and 6 observers to the Council, among which Japan, Russia, and the USA. The annual budget is about 1.2 billion Swiss francs a year. And I used to say that if you want to use more familiar units, this corresponds to about 1 cappuccino per European citizen per year. Perhaps a cup of tea in India and the member states contributes to the budget in proportion to their net national income. So, for instance, Germany has the largest NNI in Europe, so is the largest contributor to the budget. Associate member states contribute 10% of what they would contribute if they were member states, and India contributes about 1.2% of the CERN budget, with about 14 million Swiss francs a year. And this budget is used to develop, to build, to operate, to upgrade the scientific and technical infrastructure, so the accelerators, the labs, the workshop, that are used by the community of scientists from all over the world to do their physics experiments. So this community is very big. We have about 13,000 users from all over the world. You see, a large part of them come from member states, here in dark blue, but many also from non-member states like Canada, the USA, Russia, Japan. And many also come, however, from very little countries that are not really at the forefront of science. You see scientists from Nepal, from Sri Lanka, from Azerbaijan, etc. So for these scientists, of course, working at CERN is a way of developing their scientific and technological level and being brought into the circle of the big science and big technology. Some of these scientists actually come from countries in conflict, which will not sit at the same table for political discussion, but actually in science they work together. So it's also a way of fostering peaceful collaboration. India has a very strong contingent of about 400, almost 400 scientists involved in our activities. Most of these scientists come from Indian institutes here in India. Some of them come from affiliated with other institutes in the US or in other countries. And also at CERN, you have quite an important contingent of scientists in terms of staff, and in particular the young people, the fellows. So these are postdoctoral young scientists and doctoral, technical, and administrative students. So you're doing quite well proportional to what you contribute to CERN in terms of human resources and the way you use our training and educational offers. Now, if you look at the age distribution of the scientists working at CERN, so this 18,000 people from all over the world, you see that actually the peak is at 27 years. So you see that most of the CERN population is young, so the workforce is very, very young. We have about 40% of our scientists below 35. Of course, there are tails, but there are very many young people. We have at each moment in time more than 3,000 PhD students. And the female components was mentioned in one of the previous speeches, in particular the one on from DST, head of DST. Today at CERN, the fraction of female scientists is about 20%. So physicists and engineers. There is still a long way to go. But if take into account that in 1995, about the time I joined CERN, we were less than 8%. So there's been quite a large progress. So perhaps I can expand a little bit. We have a larger fraction in the young generation, about 40% of at the level of student and postdoc. Then of course the fraction goes down due to what we call the leaking pipe. So the fact that at some point, at some stage of career, women feel that they cannot, reconcile their private life with their professional life at the forefront of science. So there are many things that we can do, like for instance having infrastructures that help the young women to find strike the right balance between life and work. So at CERN, for instance, we have a creche, we have a nursery for kids. Now we are going to build a second one. So infrastructure to allow young families to have a professional, rewarding professional life. And the other important thing that we have put in place is monitoring the career. Make sure that women and men advance at the same level, and for the same work you get the same kind of not only salary but also professional recognition. Now, when we have all these young people at CERN, but only a small fraction of them stay in research in particle physics. Typically, only 10% of them, because the number of jobs in research is not that large. So 90% of them go elsewhere, and if you look at where they go, 40% remain in the public sector, governments, other international organizations, and about 50% go to industry, private sector, so communications, finance, engineering. So if you can see that actually most of our people actually go elsewhere. So it is our mission and the mission of the institution collaborating with CERN, so DST and the Atomic Energy Commission in India, to prepare the young people in our field for any walks of life. So we have this mission also of preparing them for industry and for other activities. So because we have so many young people, of course, education and training is one of our primary missions. So we have been running now for decades schools, of course, for particle physicists, for accelerator physicists, for computer engineers, so for the people who work in our field. So this school started initially in Europe with a joint effort between Europe and Russia. But then we also moved to Latin America and recently also to Asia. And actually the first Asia-Europe-Pacific school was held in India, in Puri, in 2014. So we tried to get the work together, and more recently also in Africa. We also have many initiatives for non-scientists, so for high school kids and high school teachers. We have in particular a very successful teacher program. Every year we welcome at CERN about 1,000 high school teachers. It's a very successful program. India, until now, didn't have a strong participation in this program. We think that it can be larger, so we will solicit you to participate more, because, of course, it's very important to promote STEM education, science, technology, engineering, and mathematics. And, of course, the teachers are multipliers, because behind the teacher there are many students. So if the teachers get, excited with the science we do, of course, then the kids will follow. And but recently we also had a very nice initiative of creating a program of education for South Asia. And the first pilot, organized in association with CERN, was actually held here in India, in New Delhi, in April this year. So this is one of the initiatives that we try to promote also science with in high schools, and not only the university level, but also at the high school level. Every year we welcome at CERN under 30,000 visitors. Most of them are high school students, and about 80% come from more than 700 kilometers away. So these are not just local tourism, but these visitors come from all over the world. But we receive 300,000 requests that we are not able to satisfy. So now we have some programs, an initiative to expand our educational offer with some dedicated projects. So I now go back to our primary mission, which is science. So our goal is to study the elementary particles, among which we find the building blocks of matter and of the universe as we know it today. So I don't need to recall you that matter is made of atoms, which are in turn made of a nucleus surrounded by electrons, and the nucleus is made of protons and neutrons. And protons and neutrons are not elementary particles. They are made of smaller constituents called the quarks. And as far as we know today, the quarks and the electrons are elementary particles. They cannot be cut into smaller pieces, and so therefore they are the elementary constituents of the matter that we know. So all of us here, we are all made of electrons and quarks. Even Professor Vias, with all due respect, you are made of electrons and quarks, as all of us in this room. Now, the modern accelerators, and the Large Hadron Collider is the most powerful accelerator we have today, allows us to study matter, so to probe matter at the level of the quarks. So at the level of smaller than 1 billion of a billion of a meter. So these are the scale, the physical scales that we are probing with the Large Hadron Collider. At the same time, this understanding of the very, very small allows us also to understand the very, very big, so the evolution of the universe. And the reason is that at the beginning of the of the universe at the time of the Big Bang, which is the big explosion that gave origin to the current the universe about 14 billion years ago. The universe was a very, very hot ball, very dense and hot ball, made essentially of three elementary particles. So by studying the elementary particles and their interaction at the most fundamental level, we can understand how the early universe behaved. And then with time, the universe expanded and cooled down, and so this brought the elementary particles to get together to form first neutrons and protons, then nuclei, then atoms with nuclei and electrons together, and then molecules up to the big structure that we see today, so stars, galaxies, planets, etc. And as we have seen also in the previous presentation, there are several complementary approaches to study the universe, and mainly two complementary approaches. One is to use telescopes on Earth or in space, and the telescopes looks at the big objects, and by looking at them, they try to understand how the universe developed. And by looking at the farthest object, they can go back in time, close to the origin. However, there's a kind of wall about 380,000 years after the Big Bang, and telescopes cannot really go back to earlier epochs. The reason is that for earlier epoch, the universe was so dense that it was opaque. The light could not escape out of this dense ball of particles, and therefore never reach us and our telescope. So to go to earlier epochs, we need to use particle accelerators. And the largest accelerator ever is the Large Hadron Collider that you can see here in this nice picture that shows the Geneva region with the Alps, here the Mont Blanc, Lake Geneva. Here you can see this white dashed line shows the border between Switzerland in the upper part of the screen and France here below. And here you can see this yellow ring, which indicates the location of the Large Hadron Collider. So it's a 27-kilometer ring, 100-meter underground. And as mentioned before, we have been since 2010, when we started operation, we have been running and accelerating two beams of protons in the two opposite directions up to the highest possible energies afforded and allowed by technology, and then brought them into collision at 4 points of the ring, where we have installed in 4 big underground caverns 4 experiments called ALICE, ATLAS, CMS, and LHCb. And the role of the experiment is to record the products of the collision. So the two proton beams collide at the highest possible energy. In the collision, many things happen. New particles can be produced, like the Higgs boson, or just the protons goes into 1,000 pieces, and you can study their substructure, the quarks, and the gluons that keep the quarks together inside the protons. And so the goal of the experiments is to detect the particles produced in these collisions. We talk about thousands of particles for each collisions, reconstruct the trajectory of every single particles, identify those particles, measure their energy, and so to have a kind of picture, a photograph of the collision event that allows us then to interpret it and understand what happened during the collision. So the detectors can be in some sense thought as giant digital camera that takes picture of the collision, but they have to be very fast because the two beams of protons collide 40 million times a second. So it's really quite challenging. Only 2 years after the startup of operation in July 2012, ATLAS and CMS announced the discovery of the Higgs boson, which is a very special particle for the reason that I mention later on. India has been, as I will mention later on, has been heavily involved in all components of the LHC project, from the accelerator itself, with the production of superconducting magnets and power supplies and precision jacks and etc., to two big experiments, CMS and ALICE, to the computing infrastructure with two important centers here in Mumbai and Kolkata. The Large Hadron Collider and Higgs experiment, as well as the computing infrastructure, required the development of new concepts and new technologies that were not known when we started the project in the early 90s. So, for instance, here you can see a spectacular view of the underground ring. So you see the tunnel, 27 kilometers. It looks very similar over the full circumference. You can see here these blue tubes. These are warm vessel which contains superconducting magnets. So the single most important ingredient, technological ingredient, that allow us to make a big step in energy compared to the previous collider, which was the Tevatron proton-antiproton collider at Fermilab in the US, was the development, it's been the development of superconducting magnets that allow to guide and keep the proton in the orbit of the ring. Because the most difficult thing in a proton accelerator is not to accelerate the particles. This is quite easy for proton beams. What is difficult is to confine the protons in the racetrack of the ring, and to keep the orbit at the level, in its theoretical trajectory at the level of a few microns. And so this requires very powerful magnets, because of course if the protons have a very high energy, the higher the energy of the protons, the more difficult it is to keep them inside the ring. So superconducting magnets, because we needed to transport currents at the level of 13,000 amps. And so it will be very inefficient to transport this current with normal conducting material like copper. So we use superconducting materials that show essentially no resistance, but materials become superconducting when they work at low temperatures. So we have developed 1,200 superconducting magnets based on niobium titanium working at 1.9 Kelvin. So minus 271 degrees centigrade. This was a big jump in technology. Even today, these are the cutting-edge magnets if we deploy them on a 27-kilometer machine. Of course, now we are already developing new generation of superconducting magnets based on other materials, but at the moment we are at the level of just a few units and not 1,200 magnets. So these magnets were built in collaboration between CERN and leading industries in Europe, which then, which work with us in the development of the prototypes. And then once the prototypes were at the level of requirements needed for the collider, then we transferred the knowledge to industry and they built it. So this is one shining example of what the partnership between CERN and industry can do. Just to tell you that we say that the Lhc is one of the coldest places of the universe, because if you ask yourself what is the temperature of the universe today, 14 billion years after the Big Bang, the average temperature is 2.7 Kelvin, and we operate the Lhc at 1.9 Kelvin, which is the temperature of superfluid helium. And so we used to say that the Lhc is the coldest place of the universe and also the coolest place of the universe. Okay, so the detectors, the experiment, are also very impressive. So this is a view of the Atlas detector. You can see the size of two human beings, and these detectors contains hundred millions of silicon sensors. They use 3,000 kilometers of cables to transport the signals from the detector to the control room. So clearly a large development of massive new technology. So the question is why? Why did we decided to embark in this great adventure? And the reason is that the LHC has been built to address some very important open questions in fundamental physics. The first one, which is related to the Higgs boson, was related to the origin of the masses of the elementary particles. So where do for instance, the quarks and the electrons get their masses from, and why this is important, I will tell you later. So now with the Higgs boson, we have understood at least part of the problem, not fully, but the discovery of the Higgs boson allows us already to make some step forward in understanding the origin of the particle masses. But there are some additional questions that are outstanding today, and they were also alluded to in the previous presentation. So, for instance, today we only know 5% of the universe. When we look at the sky, what we see is just 5% of what is out there. The rest is made 95% of form of energy and matter that we don't know, and so we call them dark energy and dark matter. And so the LHC strive, for instance, to understand what is the composition of dark matter. If dark matter is made of certain kind of particles, we may be able to produce them in the collision of the proton beams. Also mentioned before, the so-called matter-antimatter asymmetry. We think that when the universe had origin 14 billion years ago, matter and antimatter were present in the same proportion and same amounts, but then nature favored matter over antimatter, so antimatter disappeared, and today we live in a universe that is almost exclusively made of matter. So where did the antimatter go, and so on and so forth. So following the discovery of the Higgs boson in 2012, the Nobel Prize in Physics in 2013 was given to François Englert and Peter Higgs, the two theoretical physicists that in the early 60s predicted the existence of this very special particle. Why is it so special? I alluded to the fact that the Higgs boson is related to the mechanism by which the elementary particle acquire a mass. And now, if the elementary particles that are the fundamental constituent of atoms, so the electrons and the quarks, do not have a mass, then atoms will not exist as bound states, will not stick together. And so the matter of which we are all made will not exist. So even ourselves, we will not be here, or perhaps we will have completely different shapes. So this is very important. Let me also stress that when we talk about the Higgs boson, there are two components in the Higgs boson. The Higgs, of course, itself, we know, so Peter Higgs, who predicted this particle, but also, of course, the name of Satyendra Bose, who developed the theoretical understanding, the theoretical theory that underpins the behavior of a system of particles called bosons that have some specific quantum number. So I wanted to mention this very important contribution. So what about the future? So at the moment we are running the Large Hadron Collider. We are also thinking of, we are not just thinking, we are upgrading the collider to work with more intense proton beams to produce 10 times more collision than the original LHC project, which will allow us to, for instance, to produce heavier particles which have tiny rates, or to study processes that are extremely rare. So this is a fact. This is now being realized. It's an ongoing project. We also have some design studies for future project, post-LHC project. These are not yet approved. These are at the level of design studies and R&D. One is the so-called compact linear collider, CLIC, and India has been very much involved, in particular in demonstrating the new accelerator technology related to CLIC. So this will be a linear collider where the two beams come from the two opposite sides, and the beams are electrons and positrons, and they collide in the middle. So you see here the racetrack on the slopes of the Jura next to the Geneva Lake. And the other one is called FCC, Future Circular Collider, so it will be a ring like the LHC, but bigger. So you see here the LHC ring, 27 kilometer, and the FCC ring, which will be a 100-kilometer ring in the Geneva-Ottawa region, and would provide electron-positron, and proton-proton collider at energies up to and more than 7 times the LHC. So before concluding, I would like to mention that very often I'm asked the question if the Higgs boson will change our life, and my answer is that it already has, because I try to show you that our scientific goals require very ambitious and complex technologies that then find application in society. So the technologies developed at CERN find application not only the World Wide Web that I mentioned before, but in the analysis of historical relics, material science, solar panel, and also in medical application, for instance, in medical imaging. The PET scanner, which is one of the most widely used scanners, is based on technologies developed at CERN, but also the use of protons and light ions like carbon ions to bombard the tumor in a way that is much more localized and focused than X-rays that split and spread all over the places. And these machines are based on CERN technology. To conclude, a few words about the partnership, the very strong partnership between India and CERN that dates back to the early 70s, pioneered by TIFF. the institute in Tata Institute in Mumbai, and which of course saw a very strong participation of India in the Large Hadron Collider. But not only, you are very much involved also in other very important program, particularly in nuclear physics. As I mentioned before, you have given made very important contributions to all the aspects of the LHC, from the accelerator to the experiments and the computing infrastructure. You were awarded, because of your important contribution, the status of observer in 2012, and as of January 2017, you are an associate member. So you have a strong involvement in ALICE and CMS with a large number of institutions, and you have really built very important component of this detector, showing also a strong partnership between scientific institutes and universities and your industry. And I would like to conclude with a very nice mention of a beautiful competition that we have at CERN, which is called Beamline for School. Every year we launch a competition among high school kids and schools and from across the world, and we ask them to propose a project to then be run at a beamline at CERN. And the projects come from schools all over the world, hundreds of schools, and every year we award the prize to 2 teams, and these 2 teams come to CERN, and then they implement their project at our beamline with the help by our scientists. And in 2018, the competition was win by a school in the Philippines and a school in India, in Mumbai. And here you can see the happy team at CERN. Okay, thank you very much.
Thank you very much, ma'am, for giving an insight into the research and educational activities of CERN all over the world. Now, as a token of our appreciation for their valuable time and contribution, we would like to present mementos to the invited guests. May I now request Shri K.N. Vyas, Chairman, AEC and Secretary, DAE. I request Shri K.N. Vyas, Chairman, AEC and Secretary, DAE, to present a memento to Dr. Fabiola Giannetti, Director, DG and CERN. Now I request Shri Arun Srivastava to present a memento to Dr. K. Kasturi Rangan, former Chairman, ISRO, and it's okay.
Thank you.
Okay, once again, I request Shri Arun Srivastava to present a memento to Shri K.N. Vyas, Chairman, AEC and Secretary, DAE. Once again, I request Shri Arun Srivastava to present a memento to Dr. Praveer Asthana on behalf of Professor Ashutosh Sharma to receive it. Okay, now I request Dr. Praveer Asthana to present a memento to Shri Arun Srivastava, Secretary, AEC and Head, ICPD, NCPW, DAE. Now, once again, I request Shri Arun Srivastava to present a memento to Dr. Praveen Asthana. As we come close to the event, I would like to call Dr. Praveen Asthana to propose vote of thanks.
dignitaries on the dais and off the dais and friends. I think it's still good morning. So very good morning to all of you. It is my proud privilege to propose a vote of thanks at the end of this important program. First, our sincere thanks to the chief guest today, Dr. Fabiola Gianotti, the Director General of CERN, for taking some time off her busy schedule and coming all the way from Geneva to visit Vigyan Samagam and deliver an inspiring public address. When it comes to mega science projects today, the first name that comes to everyone's mind is the Large Hadron Collider at CERN. In some sense, it has become a symbol of what mega science is all about, of years of painstaking work undertaken by thousands of scientists from all across the world, amidst all the developmental uncertainties of a project pushing the very frontiers of technology, and of the accelerating joy and excitement that comes with discovering yet another secret of our universe. CERN is also now synonymous with the World Wide Web, which has revolutionized the way we communicate and do business today. Madam, we are extremely thankful to you for sharing with us a first-hand account of the challenges and joys of pushing cutting-edge science at such facilities. Our sincere thanks to Dr. K. Kasturi Rangan, former member Planning Commission, former chairman ISRO, and former Secretary Department of Space. Dr. Kasturi Rangan has been a champion of mega science in India and has guided the evolution and implementation of several such projects and also the policy framework for mega science during his tenure at the Planning Commission. In fact, all the mega projects that we have started in recent times were recommended during his tenure in the Planning Commission. Sir, we are deeply indebted to you for your contributions to the cause of mega science in the country. Thanks once again for agreeing to grace this occasion. Shri K.N. Vyas, Chairman, Atomic Energy Commission and Secretary DAE, and Professor Ashutosh Sharma, Secretary DST, who could not be present in person today, lead the mega science program in the country, as most of these projects are joint DAE-DST projects. Without their constant encouragement and guidance for such large-scale and long time-scale projects cannot be implemented. Thanks to both of you, sirs. Our sincere thanks to friends from the media for spreading awareness about such projects in the country. Thanks to Sri Arun Srivastava, my colleague from DAE and the convener of Vigyan Samagam. His immaculate and detailed planning of Vigyan Samagam and the energy he has infused in all the related activities have been admirable. Thanks to all my colleagues from CERN, NCSM, DAE, DST, and various project groups, guests from scientific institutions from Bangalore and elsewhere, guests from industry, esteemed members of the public, and dear students who have made this event memorable. Thanks one and all.
I'm taking an additional minutes and continuing with what Praveer said, because I want to especially thank Charlotte, who has come from CERN, and she is the person with whom India is in touch with for all the programs that we do it with them. Thank you very much, Charlotte, for making it. Again, you traveled along like Fabiola. And I would also like to thank Jerome, who has come specifically to look into what India can offer in terms of industry. And yesterday he had a good visit to one of the industry and had several bilateral discussions with many of the people. So thank you very much for making it and making us aware, right? Thank you. So now we go to the exhibition area. I think that's the most interested thing. Of course, we heard all good speakers. So we can join from here. It's in the 3rd floor. So some of us will have to climb. I hope you people don't mind it, right? And thank you very much for being here for this inaugural program. Sorry, there's one more announcement. A lunch has been arranged in the 2nd floor of this particular complex. So I request all of you to please join for lunch.
So perhaps we should discuss later on what the step we can take. Very good.
ಇದೆಲ್ಲ ಏನಿರಬಾರ್ದು ಕಂಪ್ಲೀಟ್
ಇವಾಗೇನು ಈಗ 1:15 ಬಂದರೆ ಸಾಕಲ್ಲ ಇದೆ ಸಾಕು ಓಕೆ ಬಟ್ ಲೇಟ್ ಆಗಬಾರ್ದು ಅವ್ರು ಆ ಕೆಲಸ ಹೇಳ್ತಾರೆ ಈ ಕೆಲಸ ಸರ್ ನಾವು 1:15ಗೆ ಇದ್ದೀವಿ 1:15ಗೆ ಇರಿ ಏನು ಮಾಡಿ ಅಂದರೆ ಅವ್ರು ಲೆಕ್ಚರ್ ಶುರು ಮಾಡ್ತಾರೆ 2 ಗಂಟೆಗೆ ನೀವು 1:15 ಇದೆಲ್ಲ ಈ ಕಡೆ 1:15 ಅಥವಾ 1:40ಗೆ Yes, so we have made it special because we had some issues. There were some challenges in terms of the size of the exhibition for the venue that was chosen. So we've now come up with a custom-made solution for the day venue. So this this accelerating science will connect, but we have a slightly smaller version that is custom and particularly tailor-made for the venue day, which means that we will also have a very nice presence in venue. Slightly smaller, but the best bits of this exhibition will also be in venue. So that means that we will be throughout, so we will have the all four videos, which is very nice.
Hello, please. Arun, please, just give me a second. Give me a second. So, ma'am, come here. Yeah. The iconic picture. If not in Cern, then here. And look here. Smile, kid. You are the godmother. Appreciate that, ma'am.
So here we are in the LHC, 100-meter ground under the ground, and this is the world's largest particle accelerator. The objective is to collapse the particles in the center of the four experimental particles. To accelerate the beam, we are using electrical field created by radio frequency cavities in one place of the tunnel. The rest of the tunnel, the 27 kilometer, it's filled up with magnets. The magnets are used to keep the particles on track, but also to focus them. We have 1,280 black holes and particles are focused and we are
That's the use of this.
Last year.
So, somebody
What we want, I'm going to present this, and Academy wants a picture. I will give it to you. Yes, I am giving you the Observatory sciences. I issue our and they wanted me to present it to you. Thank you. They actually wanted an interview with you, but since there is not enough time, thank you very much. Thank you. Thank you. So, at least you can carry that. You can carry that. Yeah.
ಸರ್ ಈ ಕ್ಯಾಮ್ರಾ ಜೂಮ್ ಅಂದರೆ ಫೋಕಸ್ ಆಗಲ್ಲ ವೈಟ್ ನೋಡಿ ಸರ್ ಜೂಮ್ ಓಕೆನಾ ಫೋಕಸ್ ಆಗುತ್ತೆ ಸರಿ ಫೋಕಸ್ ಆಯ್ತಾ
He is one of our best science journalists.
Stand there, no? You can stand. I'll take a photo.